Saxon Advanced Mathematics, Lesson 18, Greeting Students. We're going to talk about advanced word problems today. This is a collection of word problems that we all covered last year in Saxon Algebra 2, which all of you completed that course, so you've already learned all of these different word problems. We're just going to review 7 different types of them today and drown you in fabulous memories about how to do this. The one rule that I want you to remember is that the number of variables that we use to set up a problem drives the number of equations we need to solve it. However many variables we have, we need that same number of equations, okay? So we always take care in the way that we set up our problems to minimize the number of variables so that we can create enough equations to do with it. That's my only preamble. Let's just jump in and start working these. The first one is, well, let me just read it to you. The number of blues was 4 less than the sum of the whites and the greens. Also, the number of greens equaled the sum of the blues and the whites. Do you feel the headache coming on? I do. How many of each were there if there were twice as many blues as whites? So what we hear right away is that we've got 3 variables based on these colors, right? John likes to use a subscripted variable. Number of blues, number of greens, number of whites. That is his preferred method of setting up the variable, which I understand because what he's saying is, let's take the words of the sentence and really make that match to the variable. And I don't disagree with that. I think that's great. And in some cases, this is really important. For example, in coin problems, it's very important that we differentiate between the number of something and the value. But this problem is not like that. We're just talking about these items. So I am also perfectly fine if you want to simplify this to just be the letters that represent the colors. And that's the style that I'm going to use. All right, so let's start working on these equations and we'll just tackle each one as they go. The number of blues was 4 less than the sum of the whites and the greens. Okay, now watch the way I'm going to write this. The number of blues was 4 less than the sum of the whites and the greens. Sum tells us to add it. And what I've written here, I know isn't right because I'm not done yet. It's an inequality. And notice how if I leave out the number, less, the number of blues was less than the sum of the whites and the greens. I do this intentionally, you guys. I write an inequality first because it helps me remember how to use that number to balance these two sides. I can see by this inequality sign, which was driven by the word less in the sentence, B is the lesser, this side is the greater, right? That's what my inequality tells us. So I know 4 is the number that will make it balance. So I can either add 4 to the lesser side or I can subtract 4 from the greater side. My preference is always to make the adjustment here on the right where I've got room to spread out a little bit. So I see this side is the greater, 4 is the number that balances, so I'm going to subtract 4 and change that into an equal sign. Okay? Tricky, but these statements are kind of tricky. The next one's a little more straightforward. It says the number of greens equaled the sum of the blues and the whites. The number of greens equaled the sum of the blues and the whites. Okay, that one's easy. Here comes another one that can be very confusing. How many of each were there if there were twice as many blues as whites? Twice as many blues as whites. So that tells me, once again, let's write the inequality. There are more blues than there are whites. I know I have to multiply something by 2, but so often we get trapped into thinking, oh, it's twice as many blues as whites. But that doesn't create an equation. If we want it to balance, then we have to multiply the smaller number, which my inequality clearly shows. We have to multiply this side by 2, right? If there's 10 blues and 5 whites, that's twice as many blues as whites. We have to multiply the small side to get it to work. Okay, so here's my system of equations. There's my 3 that I'm going to start with. And there are many ways to use substitution and elimination. We know we're going to need a couple steps to get it to work. But I'm going to start by substituting C into A and B. All right, so this expression can be substituted in. So in the first one, I'm going to get 2W equals B. So 2W equals W plus G minus 4. And then in the second one, I'm going to get G equals 2W plus W. Huh, okay, I like it. So this is our new A and B. And we've used equation C, so we don't have to worry it anymore. Now, step 2, I'm going to rearrange into the format of number of greens plus or minus the number of whites equals a plain number. Okay, so essentially what I'm going to do, I'm going to swim the G and W terms to the left, and I'm going to swim any plain numbers to the right. If you have not heard the story about my first algebra teacher, his name was Jerry LaCrone, Mr. LaCrone, and I have a picture of him from my middle school yearbook. I'm going to treat you to him. But he came up with this whole thing about when you're moving terms in algebraic equations, it's like schools of fish. And in the beginning, they're all intermingled with each other, the G fish and the W fish and the plain number fish. And then, you know how when danger strikes, fish quickly separate and reconnect with their schools of fish? That's what's happening. This is just a happy day in the coral reef, and then the shark swims by and everybody goes to their friends. So what we're going to do is we're going to swim the G's and the W's to the left, and we're going to put the plain numbers over there, and it's going to be good. So let's take the first equation again. 2W equals W plus G minus 4. And we're going to push... We're going to add a W and we're going to add a G. Oh no, I'm sorry, we're going to subtract them. Minus W minus G. And we'll get W minus G equals minus 4. See how we rearrange them? Okay, and then this was A. And then B. Let's see, I'm going to subtract 3W. I'll write it out. What the heck? I'm changing from uppercase to lowercase. I don't know why. So we're going to subtract 3W and swim that across. And it looks like I changed my mind. Instead of having the G's first, I'm going to have the W's first, right? So I'm going to write minus 3W plus G equals, and then that's all gone. It's just 0. I don't know why I changed to lower cases. That's kind of weird, isn't it? Okay, so now we have a new system. I'm going to write this at the top of the next page. W minus G equals minus 4. I'm going back to upper cases. And minus 3W plus G equals 0. I'm sure I got that right. I'm just checking my work there to make sure I copied correctly. But this is our new system after we rearranged it. Get myself back in camera range there. And now we see that we look down the columns and say, let's talk about elimination. Remember, we're looking to see, should we eliminate the W's or eliminate the G's? The W's, we could multiply this top row by 3, and that would cancel nicely. But look, the G's are already good to go. So we don't have to adjust anything. We can simply add them as they are, and we get minus 2W equals minus 4. And then if we divide both sides by minus 2, we get W equals positive 2, right? That cancels, and that simplifies. Beautiful. Okay, so that looks really good, right? We're happy with that. Now we want to work back and fill in what the G and the B are, right? The number of greens and the number of blues. So let's use this one to solve for G. We substitute, so this is step 3. Oh, wait a minute, step 2 right here. This is our step 3. This is eliminate. And step 4, solve for all variables. Okay, so I'm going to use this one. We can use any form of the equations we created. 2 minus G equals -4. I'm going to add 4 to both sides, and I'm going to subtract G from both sides. No, I guess I'm going to add it, aren't I? This cancels, these cancel, and I get 2 plus 4 equals G. So G equals 6. And then I'm going to have to go back here to find one of my old equations with B in it. Here's one, G equals B plus W. So if I'm using G equals B plus W, and I've got those two, I can see that 6 equals 2 plus, B plus 2. That's a B. And subtract 2 from both sides, B equals 4. So there is my final answer. The number of whites is 2. I'm checking to make sure. The number of blues is 4, and the number of greens is 6. Yay! That's right. What I would do, I wouldn't bother rewriting these. Every time you rewrite something, you run the risk of making a silly mistake. So I would just box those off like that and call that good. All right. So there we have our steps, and every system of equations has its own little personality, and we want to use substitution and elimination however we can think of to do it. In the beginning, if you feel confused, it is not cheating to take a quick look at the solutions manual to have John kind of set a strategy for you. As you build confidence with these, you'll be able to make your own decisions about substitution and elimination. And again, as long as your math is error-free, you can use any strategy you want. It is a good reminder that we always want to use all 3 equations, A, B, and C. So that for sure we want to do, but there's no one way to solve them. And that is your privilege as a mathematician to decide how you'd like to do it. Okay, 18.2. The quarters, nickels, and dimes totaled 20, and their value was $1.90. How many of each kind were there if there were 4 times as many nickels as quarters? Okay, now this is a problem where we have quantity and value, don't we? We have the number of coins and we have what they're worth. For these, I like to use the variables with the n. So I like to use number of nickels, number of dimes, and number of quarters, because I'm later going to be talking about how much they're worth. And I always remember that I have a quantity statement and a value statement, and then in these problems we have a third statement that has to do with something else. All right, the quarters, nickels, and dimes totaled 20. So the number of nickels plus the number of dimes plus the number of quarters equals 20. Cool. Their value was $1.90. Now I remember that with this, what I'm going to do is I'm going to multiply the number of each coin times the value of the coin, and then I'm going to say that they have to equal the value. We want to make sure that we're clear because these we define in terms of cents, but the quantity is defined as a dollar with a decimal for cents. I don't want decimals in this, so I'm going to define all of this in terms of cents. So 5 cents times the number of nickels plus 10 cents times the number of dimes plus 25 cents times the number of quarters equals $1.90, but I'm going to write that as 190 cents. No decimals, life is good. Third one, there were 4 times as many nickels as quarters. Just like last time, I'm going to be careful with this, and I'm going to write it as an inequality first. There were 4 times as many nickels as quarters. That means the number of nickels was greater than the number of quarters. I leave space in there for adjusting. It's 4 times, so I can see this is the smaller number, so here's where I multiply by 4. There were 4 times as many nickels as quarters, so if I multiply the quarters times 4, then that'll give me this bigger number over here. All right. There's our system of equations, and now we have to think about how to use these. Now, just like our previous system, this third one is a quick and easy substitution. So let's start again. Step 1, substitute equation. Let's do these with A, B, and C as well. Substitute C into A and B. All right. Oh, I'm sorry, I didn't write this. This is number of nickels, and this is number of quarters. I switched my strategies, and I don't want to do that. Okay, so the new version of A is going to be 4 times the number of quarters plus the number of dimes plus the number of quarters equals 20, right? I substituted this in for that. And now I'm just going to quickly clean that up. Number of dimes plus 5 times the number of quarters equals 20. I like to put the coins in order by their value. That helps me keep it straight. And so I'm just adding like terms really quickly here so that I keep my equation nice and clean. B, let's substitute into there. It is 5 times 4 times the number of quarters plus 10 times the number of dimes, 25 times the number of quarters equals 190. Again, I just substituted in here. The 5 is on the outside, and then we have the 4 NQ in there. So let's clean this one up as well. This would be 20 times the number of quarters. And when we clean that up, we'll have 10 times the number of dimes, which is here. And then we'll put these two together. That's 20, that's 25, so we say plus 45 times the number of quarters equals 190. Okay, so now, just to help me see it more clearly, I'm just going to put a light squiggle through these so I don't get confused with what I'm looking at. I'm comparing these two. Step 2 is to eliminate A and B. Okay, so again, I'm going to look down the columns and I'm going to figure out what's the easiest way to eliminate this. Let's see, these guys, I could multiply this top one by minus 10. That would make these eliminate. Or I could multiply this one by minus 9. That would give me 45 here. And those would eliminate. I would rather multiply by 10 than minus 9, minus 10 than minus 9. So I'm going to multiply all of this by minus 10. Let's do that. Minus 10 times the number of dimes, minus 50 times the number of quarters equals minus 200. And then this one stays the same. 10 times the number of dimes. I'll give you a second to catch up and catch your breath. But again, we chose to eliminate the dimes because that would require us to multiply by 10, and that is easier than 9. It's just less likely to make a mistake, right? Okay, so now we eliminate them. We add, these cancel. This gives me minus 5 times the number of quarters equals minus 10. Oh, I love it when it comes out even. And you know what, you guys? These problems, I've never seen one that doesn't come out cute and perfect. Divide by negative 5, and we get the number of quarters equals 2. I'm just going to go ahead and box that now. The other numbers might float around on my page a little bit, but I'm not going to worry about it. I hate to switch. I hate to flip my page when everything's right here. So step 3 is solve for the other 2. I'm going to go back to this and say, oh, okay, so the number of nickels equals 4 times 2. So the number of nickels equals 8. I'm just going to write that over there so I can use that part of my paper and have a really clean, simple answer. And then for the third one, let's see, let's use this for our final one. The number of nickels is 8. The number of dimes we don't know. The number of quarters is 2, and they all add up to 20. I subtract 10 from both sides, and so then I get the number of dimes equals, because this all cancels, right? 20 minus 10 is 10. So it's perfectly fine to box your answers separately. This is not an ordered triple like sometimes we get when we solve it for X, Y, and Z, so we don't have to write them all 3 together. We just want to make sure that we have each coin clearly identified, and I'm just double checking. Quarters is 2, nickels is 8, and dimes is 10. Great. We got the other one right. I don't think I smiley faced it. Okay, that's a bonus coin problem where we have a quantity statement, a value statement, and then one more statement because we need 3 equations because we have 3 variables. All right, hanging in there. Take a breath, you guys, between problems if you need to. Pause me, walk around the block, ask your mom what your family's doing for Christmas, you know, whatever it takes to clear your mind for a few minutes. So, not too long, but a while. I personally am going to plow ahead and look at the next problem. Reds vary directly as blue squared and inversely as greens. Oh, remember these variation problems? Okay, let's take a look. Reds vary directly as blues squared and inversely as greens. Remember, there are 2 ways to do these variation problems. There's direct and there's inverse. And with these, with the direct variation, we say that A is equal to a constant times B. Or if we have squared, we say A equals K times B squared. Or we can use what's called the proportion method, and we say A1 over A2 equals B1 over B2. And then we can also do that with a squared. Okay, so this is without squaring, this is with squaring. This is our constant method and our proportion method. If we're doing an inverse variation, remember with the constant method, we put the constant in the numerator and the B part of the information in the denominator. If it's squared, we just square it down there. If we're doing an inverse in the proportion method, then the left side stays the same, but the B sides flip. Remember the 1 and 2 subscripts stand for like the before and after, and John usually makes it clear in the story. And then here, we do the same thing, except we would square. Okay, so we're flipping the second variable because of the inverse variation. So this is kind of a general, this is simple variation, and this is squared variations. All right, so let's look at our example again. Reds vary directly as blues squared. Reds vary directly as blues squared. So I'm using this style of presentation. And inversely as greens. So now we're using this variation. The greens aren't squared. So we've got this, and we're combining them into one thing. Now we have two scenarios. We use the first scenario to solve for K, and then we use the second scenario to apply K to our new situation. So scenario 1, when there were 80 reds, there were 4 blues and 2 greens. Okay, let's stop there and solve for K. So we plug it into our base equation we've got here. 80 equals K times 4 squared, which is 16, divided by 2. Okay, so we can simplify this. Sorry, I was just looking to make sure I'm on track. This would become 80 equals, this simplifies to 8K. I'd rather write the numeric coefficient before the letter. Divide by 8, and we get that K equals 10. Okay, we're not done, but we've got a really great piece of information. That's my signal to myself. Don't forget that number. Now we go back to the problem and look at the second scenario. How many reds would there be when there are 8 blues and 10 greens? Okay, so now we're going to use this new data to solve for R, but we also need that K equals 10, and we plug it back into the Holy Bible for this problem. The Holy Bible. The Grail. It's the basic equation that's going to help us solve both of these. All right, so now I'm going to plug these other ones in. R equals, K is 10, B is 8, but it's squared, so it's 64, and G is also 10. Quite straightforward. And then these cancel, right? This is actually crazy easy. R equals 64. That's the number of reds. We've identified it clearly with the variable. So we're good. We're fine with that. John goes on to show you in the book how to solve using the ratio method. So let's just look at that too. I'm going to set it up on a separate piece of paper so I don't have to turn the page in the book away from where we're working. John says if you want to do it, this is the constant method. If you want to use the ratio method, then it's got this equation, which is a kind of a mashup of some of these. The number of reds would be equal to let me just read the words again so you can hear it. It varies directly as the blues squared. So the blues are going to stay with the 1 and 2 in the same pattern, but we have to put the squares on them. And then inversely with the greens. So the greens have the number 1 on the bottom and the 2 on the top. Okay? So that's the way we can interpret this problem for the ratio or proportion method. And now we just create a list of all our variables. R1, R2, B1, B2, G1, G2. Go back to the problem. The first time through, reds vary directly. Okay, when there were 80 reds, there were 4 blues and 2 greens. 80 reds, 4 blues, 2 greens. Those are all the ones scenario. How many were there when there were 8 blues and 10 greens? 8 blues and 10 greens. And we're solving right here. I'm just going to put an X there to help me know the mystery. Now, there are 2 ways you can use this formula. One is to just plug in the variables and solve. But we also see that you can rearrange the basic equation. For the desired variable. And I'll tell you what I mean by that. In this problem, we're going to be solving for R2. We could cross multiply and rearrange this so that R2 was by itself on one side of the equation and everything else was on the other side. That we often do in chemistry classes to simplify the final process. This problem has easy enough numbers that I feel comfortable leaving it in this form, but we could work this as an abstract equation problem, solve it for R2, then plug in. We're not going to do it though. So what we're going to do is we're just going to plug into what we have here. So 80 over X equals, now I have to square these. So this is 16 times 10 over, this is B2, I have to square it, 64 times 2. All right, notice that I did not do any of these multiplications to start with because I want to cancel as much as possible before I do any more of that. Here's what I want to do. I want to cross multiply next. Again, I'm not going to make these numbers into products. I'm just going to leave them here. I'm going to move this up so I have a little more room to work. So I'm going to say 80 times 64 times 2 equals X times 16 times 10. Then I'm going to divide by 16 times 10. Get that over here. That's all cancels. My X is by itself. Now I can simplify this and get my final answer. But look, you know what I see? 80 times 2 is 160. 16 times 10 is 160. So I can cancel both of these against both of these. And my final answer, X equals 64, is the value for R2. Okay? Same answer as we got last time. Different way to approach it. I'm not sure if one seems easier or harder to you, but to me they feel a lot the same. But here are the formulas that compare them. So this is the, if I add a column in here, this is the K method, and this is what I call the ratio or proportion method. I think that's what John calls it too. So that gives you all of them. And then in situations like this where we actually have 3 variables, then we have to combine these strategies to get one big equation. Okay, there, that was a fun one, right? Are you screaming yet? Go pet your dog or your cat if you've got one, or your stuffy if you don't. And I'll go on to example 18.4. You can join me there in a minute. I had a sip of my delicious grapefruit flavored LaCroix, my favorite beverage. I almost always have one while I'm teaching you lovely students. Okay, 18.4, we did these near the end of last year. The sum of the digits of a 2-digit counting number is 5. When the digits are reversed, the number is 9 greater than the original number. What is the original number? Okay, it's a 2-digit counting number. We remember that the trick to setting these up, t equals the digit in the tens place, and u equals the digit in the units or ones place. So, the original number is going to be written as 10 times the digit in the tens place plus u stands for the digit in the ones place, right? So we're just creating a place value situation here. But if we reverse the digits, then it's the digit in the units place that will now be in the tens place, so we multiply it by 10. And the digit in the ones place will be the one that was originally in the tens place. I hope that starts to sound familiar, but we're using place value here to show the original number and then what would happen if we flipped it. Now that we've got our variables sorted out, we can go back to our question and write some equations. The sum of the digits in a 2-digit counting number is 5. So the number in the tens place plus the number in the units place equals 5. That's our first equation. When the digits are reversed, the number is greater than the original number. Okay, so when the digits are reversed, 10u plus t, that is greater than the original number, which is 10t plus u. Okay, let me read that again. When the digits are reversed, the number is greater than the original number. How much greater than? It's 9 greater. Okay, so we look at our inequality, which we've written here, and we can see that this is already bigger, so let's add the 9 to the smaller size, and then we can fix it as an equation. All right? As John puts it, I always write something that isn't true first. The way I think of it is, first I write the inequality, then I balance it with that number. All right, so now we are in really great shape. What we can do is solve this first equation for either t or u, whichever we prefer, and then we can substitute into these. So let's change this. We could subtract the t or the u. Either way is fine. Let's subtract the u. I tend to keep the first one and subtract the second one. So that will end up being 10 equals 5 minus u. This is what we'll substitute into this. But I kind of want to clean this up.